um, program. So I would like to again request Imlitosi to introduce our speaker, and this hands-on session will continue for 3 hours. Uh, Particularly, I mean the resource person who will take up this session. He is a scholar, PhD scholar of Professor Pachori, and probably he'll be explaining the experiment, discuss the experiment which Professor Pachori has explained in his lecture. So I think all of you would be able to understand, and Mr. Kritiprasanna Das, the session holder, he will explain you and also will try to make you understand the nitty-gritty of the program. So I hope all of you will enjoy this session. Thank you. Imlitosi, please carry on.
Good afternoon, everyone, once again. I would like to welcome all the participants again, and especially our speaker for the fourth session, day 3. Okay, myself, Imlitushi Jamir. I am a faculty from Computer Science Department, School of Engineering and Technology, Nagaland University. Let me introduce the speaker for today. We have on our midst, we have Mr. Kritiprasanna Das. Kritiprasanna Das received the BTech and MTech degree in Electronics and Communication Engineering and VLSI and Embedded System in 2016 and 2018, respectively, from West Bengal University of Technology and NIT Arunachal Pradesh. Currently, he is pursuing PhD in the Department of Electrical Engineering, IIT Indore. Mr. Das' research interests include biomedical signal processing, EEG, time frequency analysis, and related area. He has served as a reviewer in several reputed journals. So, without further ado, let me give the time to our distinguished speaker for today. Sir, you may take your time.
Thank you, ma'am, for inviting me, and thank you for introduction. And
Thank you. Please carry on.
thank you, ma'am. Today I will discuss multivariate signal decomposition based EEG signal processing. First, I will discuss two application of that, and then I will show via programming like MATLAB programming how to extract the features from EEG signal and how to classify those. And for classification part, I will for signal processing part I will show in MATLAB, and I will share the code with the participants so they can parallelly run, and I think that if they run by themselves, then it will be helpful to understand better way. And for classification part, I will show using Python packages, so how to classify the EEG signal and all. So let me share my presentation. So is it visible?
Yes, it is visible.
Thank you. So today I will discuss multivariate signal processing for EEG signal, multi-channel EEG signal processing, and based on the feature extracted by signal processing, I will show how to classify the EEG signal. And for this, I will discuss two application. One is schizophrenia detection from EEG signal, and another is motor imagery BCI. This is the outline of this of today's presentation. First, I will introduce about signal decomposition and all. Then the motivation behind multivariate data decomposition I will explain. Then one adaptive data decomposition technique, this iterative filtering, I will explain how it is working, and the multivariate extension of this iterative filtering proposed by us I will show, and the code I will share. Then I will demonstrate how this MIF works with example, also with real time signal I will take, and I will decompose that, and I will show how why this multivariate decomposition technique is better than univariate one for multi-channel signal processing. Then there are several existing multivariate adaptive decomposition technique are there in literature. I will compare the computational complexity of the proposed multivariate iterative filtering, and then I will discuss two applications of EEG signal processing. One is schizophrenia detection, and another is motor imagery brain computer interfacing applications. Then I will conclude, and after discussing this I will go for hands-on part. This schizophrenia detection I will explain by providing the code, and if you want, then you can parallelly run the code in your desktop. So let's start. So here I have shown two signal in the right side figure, signal 1 and signal 2. So see, from signal 1, by observing carefully, that we can say that there is two sinusoid in that signal, but it is difficult to observe when the number of component is higher. So for that we go for Fourier transform. So what Fourier transform do? Fourier transform do basically decompose the signal, represent the signal in terms of sinusoids. So if we plot the magnitude of the Fourier transform coefficient, then we can see the two peak. So from this two peak, we can clearly say that this signal 1 have two sinusoidal components inside that. But signal, if we consider signal 2, the Fourier spectrum is quite similar with the Fourier spectrum of signal 1, but the time domain signal here in the left side, that is completely different than signal 1. So here the concept of non-stationary signal has came. Here if you carefully observe, the up to 2.5 around 2.5 second, one sinusoidal frequency is present, then it has been changed and another sinusoid has appeared. So the frequency content of the signal has been changed with time. That these properties of changing of any parameter of signal known as non-stationarity. Means any parameter, mean like amplitude or phase or frequency, if is changing with time, then we can say that that signal is non-stationary signal. So the Fourier transform, the conventional Fourier transform, has been widely used for many applications in many areas, but for non-stationary signal representation, Fourier transform fails to provide proper representation. So from these two Fourier spectrum in the right side, you can see that the Fourier spectrum is quite similar for the signal 1 and signal 2. Now the need of signal decomposition has came, like any complex signal, if we want to analyze that, so we can decompose the signal into simpler component. That's the properties of the simpler component will be known to us, so we can analyze based on those component, simpler component. So in this signal decomposition, there are based on the basis function we can represent, like for Fourier transform we represent the signal in terms of sinusoid. So sinusoid is basis function for Fourier transform. So depending on the selection of Fourier basis function, The signal decomposition can be divided into two broad categories. One is fixed basis and another is adaptive basis functions. In fixed basis function, we use predefined basis function. Like for Fourier transform, it is sinusoid. For wavelet decomposition, most probably you have heard about wavelet decomposition. So in wavelet decomposition, we use predefined wavelet function. But for adaptive basis, in this category will not have any predefined basis function. Instead, the basis function has been derived from signal itself. In 1998, first this empirical mode decomposition has been proposed, this kind of adaptive decomposition technique, and then it draws the attraction of many researchers. This empirical mode decomposition has been cited. This paper has been cited around 30,000 times and has been used in various domains, including biomedical signal processing, speech signal processing, and machinery fault diagnosis, and in many areas. Then this to overcome the drawback of empirical mode decomposition, there are a few drawbacks, like there is no mathematical proof how it is working, what kind of filter bank it is using to extract the basis function or component. uh, so several researchers has been tried to come up with the adaptive decomposition technique, but that have mathematical description and all those things. So in similar category, empirical wavelet transform or iterative filtering is there. In adaptive basis function, we represent the signal in terms of AMFM modulated oscillation. What is AMFM modulated oscillation? That is amplitude and the frequency of the signal will vary with time. So here it can be mathematically modeled like AT is the amplitude, and that is varying with time with respect to t, and phi t is the phase of that signal ut, that is also varying with respect to time. So that gives the frequency modulation property. So ut is basically a AMFM component. In several it has been termed in several ways, like modes, components, or intrinsic mode function, etc. So to be intrinsic mode function, it should follow two conditions. That is, AT should be greater than the instantaneous amplitude AT, that should be greater than equals to 0, and also the derivative of the phase, that is instantaneous frequency, d phi t dt, should be greater than equals to 0. And now based on this ut as a basis function, we can represent any signal. So here I have shown that for univariate modulated oscillation, let's consider xt have multiple component of AMFM component. So we can represent that as AIT e to the power j phi it as a summation of all those components. We can represent xt. So to find this AIT e to the power j phi it, we use this kind of adaptive decomposition techniques: empirical mode decomposition, empirical wavelet transform, variational mode decomposition. We'll briefly describe those techniques, and then I will go for iterative filtering. And now this is univariate signal xt. So if xt becomes a multi-channel signal or multivariate signal, so this technique fails to generate some fails to attain some criteria. So for that, so the concept of multivariate signal decomposition has come. And in multivariate signal decomposition, we can represent xt using similar kind of amplitude frequency modulated component in direction or dimension. And this is for monocomponent signal. That means in one direction only one component AMFM component is present. So but for real-time scenario, the real-time signal like EEG signal or any real-time signal will have multiple AMFM components. So we this mathematical model has been extended for multiple component, that is multivariate multi-component signal. So for this model, this signal have p component in each direction and have in direction in channel signal. So based on this mathematical model, so we can represent any multi-channel signal. So here, why we are going for multivariate signal decomposition instead of univariate decomposition, that has been already gained in lots of popularity, and it has shown very good performance in several applications. So we will discuss in this slide. Due to advancement in sensing technology recently, the acquisition of multi-channel data has been much more easier. So here I have shown three example, that is only few example I have shown. There is a infinitely large number of example of multi-channel signal. In the left figure, in figure A, uh, here for machinery fault diagnosis, we can collect the vibration signal from different part of the system. So we can analyze, we can assess the condition of the of different part of the system properly. And here in the figure B, that is electroencephalogram encephalogram signal. So today I will discuss it in detail in later slide. Electroencephalogram records the electrical activity of the brain by placing non-invasive electrodes on the scalp. It may be invasive also, but non-invasive EEG is much more famous and easier to obtain. And here in figure C, this is showing the ECG recording system. So by placing different electrode on the chest, we can collect the ECG signal to assess the condition of the heart. So if we collect from one part, like from like V1 V2 this location, so we can assess the condition of the heart for that particular region. But if we want to assess this the posterior portion of the heart or anterior portion of the heart, so for that we have placed a six electrode total, V1 V2 V3 up to V6. So these are the few example of multi-channel signal. So if we process this signal using univariate decomposition technique, then some problem will occur, like if there exists some mutual information, then that may lost. Another thing, in multivariate data decomposition technique, it gives the AMFM component, and for univariate processing, this number of component for each channel may be different from other channel, so that it will be a problem. Another, like frequency content of a particular mode may not be similar to another channel's mode. So we go for multivariate decomposition, which give proper mode with frequency alignment property. So, participant, if you have any doubt, you can ask in between. You can interrupt. Otherwise, I can continue. So, so first in 1998, this empirical mode decomposition has been proposed. It does not have any mathematical theory behind that how it is working, or the convergent of this has not been proven by mathematical derivations. And briefly, I will describe how the steps involved in empirical mode decomposition. So if we take any signal xn here in the right side figure I have shown. So first we have to find the extrema of the signal and by interpolating those extrema, we'll have envelope that corresponding to maxima, and we have to find a minima of the signal. So by using that, we can construct another envelope corresponding to minima. By taking average of the extrema corresponding to minima and maxima, we can get the mean envelope. Here the extrema corresponding to maxima I have shown using green color, and using red color I have shown the extrema corresponding to minima position, and the mean in envelope has been shown using the light blue color. So after this after getting this mean envelope, we can subtract it from the signal. That is basically the low frequency part. In this way, if we repeat this process until some stopping criteria has not been satisfied, will not satisfy, so then we will get the high frequency oscillatory part, pure oscillatory part, and the lower frequency part will be separated out. And after that, we have to subtract this d and the high frequency part as a signal IMF, and after subtracting the IMF from the signal, original signal itself, like xn minus dn, we have to repeat the same procedure for further extracting the other IMF also. So in this way, we get like here 8 IMF, and last IMF I have shown that is basically residual signal that does not have more than one, only one extrema can be there. So this is univariate. So this univariate empirical mode decomposition has been extended for multivariate one using several approaches. One is complex EMD, then bivariate EMD, and then the general extension as multivariate EMD has been proposed. In complex EMD, let's consider it is a spectrum of a signal. That's a positive frequency part, that because it is complex signal, so this will have separate different component in positive and negative frequency part. So here in this approach, in complex EMD, they have separate out the complex positive frequency part and the negative frequency part, and on the positive and negative frequency part, they have separately apply the EMD. So for separating out, they have taken a filter, that is the filter response is h e to the j omega. So using that, the signal can be filtered out, then positive frequency part will be separated out, and if we take the conjugate of the signal, then the frequency will be frequency response will be altered or mirrored. Then the negative frequency part can be extracted out using that same filter. So on the positive frequency part and the negative frequency part, we can apply the same EMD algorithm for getting the IMF. But the disadvantage of this algorithm for extending the complex EMD of a bivariate signal, for the number of IMF for positive and negative frequency will not be same, and there will not be any meaningful interpretation of instantaneous frequency, and this approach cannot be generalized beyond complex or bivariate data. So later another approach has been proposed. Here they have used a concept of projection. So here one signal has been, I have shown imaginary part, that is also complex signal, that all means bivariate signal. So real part and imaginary part. So this blue line is a signal that have two component. So using this approach, this complex bivariate EMD, we basically project the signal in different direction, like here yellow dotted direction. So if we project those, so then we can get a mean. If we take the mean of this 4 dot, that will be the red one, then we can interpolate to get mean in envelope kind of thing for bivariate signal. So after subtracting this mean, in the similar way we can go for decomposition for bivariate signal, and this concept can be extended for a multivariate signal also. But a drawback of this, like if we considering the four direction or considering eight direction, then the mean will be different, and the decomposed component will also be different. Based on choosing the parameters, the output will be different. And another thing, the complexity of this multivariate EMD is very high, and the number of directions should be high for getting proper decomposition. And all parallelly, the computational complexity raises for higher dimension of projection. So another decomposition techniques, empirical wavelet transform, that use the concept of empirical mode decomposition. It tries to decompose the signal into AM/FM component, and also use the concept of wavelet filter. Means it uses the filter bank based on wavelet theory. So the problem that for EMD, it was a problem that the filter response will not be clear for us, but empirical wavelet transform so proper filter response. This univariate empirical wavelet transform has been extended for multivariate one. So for that, in empirical wavelet transform, on the spectrum, we adaptively detect the boundaries. So for that, we can use several technique, like scale space approach, local maximum approach. Means in between two peak, we can put the boundary, and based on the boundary we can construct the filter bank, and we can separate out the signal. And for multivariate one, here I have shown, we have taken a bivariate signal. These have one component, this channel, another channel have another component. So the concept of boundary detection has been extended for multivariate one by taking the mean spectrum, Fourier spectrum. For channel 1, it is the spectrum. For this signal, this is the Fourier spectrum, and for channel 2, this is the Fourier spectrum. So we take the mean spectrum, and on mean spectrum, we have detected the boundary, and using that boundary, we have separated out the component. So here I have shown the time frequency representation of this signal. Another technique is their multivariate variational mode decomposition. For univariate VMD, or it originally has been proposed in 2013 based on some optimization criteria, and that also has been extended for multivariate one. By modifying the optimization problem, the constant problem, by including that this is the bandwidth. Basically, you can say this bandwidth has been calculated for all channel for multivariate data decomposition. The drawback of this multivariate variational mode decomposition is that we have to know the number of mode present in the signal, but in real time it is difficult to guess the number of modes in that signal. So it should be it is partially adaptive, but it is not completely adaptive technique. Now, the various drawback of EMD, like mathematical proof or filter response, all those has been solved in iterative filtering, and it also decompose the data in similar manner like EMD. In EMD, we construct a moving average filter, and based on that moving average filter, we extracted out the mode one by one, and the length of the moving average filter will be decided by this formula. And this is L equals to alpha n by k. Alpha is a constant and n is the sample size of the data, and k is the number of the extrema point in the signal. So we can understand that, like, if the frequency content of the signal will increase, then the k will also increase, the extrema point will also increase. So in that way, from time domain signal we extract the we can understand the frequency component inside the signal, and by using this formula we can design the moving average filter data adaptively to extract the mode one by one. So for to demonstrate, I have shown here. Let's consider this is a spectrum of a signal that have three component. One this triangular one, and this half circle, and another this one. So if we calculate the number of extrema, and according to that we can design a filter, then this red one will be the filter response of the moving average filter. That moving average filter is basically a low pass filter, and if the length of the moving average filter is higher, that means the cutoff frequency will be lower. So we filtered out the signal using this moving average filter, then we'll get this all the lower frequency component as in output. And if we subtract this the filtered component from the original signal, then we'll get the IMF. And in one step this will not be possible, but repeatedly we have to perform this procedure to get a particular IMF. So when we'll get particular IMF, the highest frequency IMF, we can subtract this IMF from the original signal, and then we can repeat the same procedure to extract the remaining IMF. So this multivariate iterative filtering has been we have extended this multivariate iterative filtering for multivariate signal. So for that, here I have shown the flowchart of univariate iterative filtering. I have already described. And for multi-channel signal, we have changed, like, we have to find the number of extrema for all channel. Maybe M1 is the number of extrema for channel 1, and MC is the number of extrema for C channel. Then we have to find the maximum of this value, and based on that we can design the filter, moving average filter, and the remaining procedure will be same. And using that same filter we will perform the filtering on for all channel, so that we will get same number of modes in all channel, and the frequency content of those modes will be same for all channel. Here I have demonstrate using one example how multivariate concept of multivariate iterative filtering works. So here I have taken a bivariate signal again. That means channel did have two channel 1 data and channel 2 data. And channel 1 data have two component, and channel 2 data has one component. So if we, based on the number of extrema present in that signal, if we design one filter, so we'll get red one in channel 1 and yellow one in channel 2. So you the number of extrema will be higher for this channel, means channel 1, because the number it have higher frequency component, and the number of extrema will be higher. So the red filter will be chosen among these two filter, and using red filter we will filter the signal in both channel 1 and channel 2. So we'll get this as first IMF, this has frequency component, and in channel 1, in that frequency band there is no signal present here, so we'll not get any component. So in this way we have to subtract this IMF from original signal, and on the remaining signal we have to repeat the same process. Here you can see that for channel 1 we'll get filter here using red color I have shown, and yellow color that have a higher cutoff frequency. So this automatically this yellow filter will be chosen when we will choose the number of highest number of extrema. So using yellow filter we'll get the component here in channel 2. In channel 1 at that frequency spectrum there is no component, so in channel 1 there will not be any component. Then we have to subtract this component from original the signal, and then again we can repeat the process to get the remaining one. In this way we'll get 3 IMF, 3 modes. So I'll provide the code, MATLAB code for this multivariate iterative filtering. So you can try to decompose multi-channel signal by your own. Here I have shown an example of real-time multimodal or multi-channel signal, and the decomposition, multivariate decomposition will show one key advantages of multivariate decomposition. Here the first two row representing ECG signal, that is the electrical activity of heart, and the third row representing the respiratory signal, that is corresponding to respiration of our respiratory systems, and the fourth row representing the seismocardiogram signal, that is the vibration signal due to the vibration comes due to operation of heart the different chamber has pump, and due to that this vibration occurs. So this all four signal, this ECG signal, respiratory signal, seismocardiogram signal, somehow they are correlated, but by observing this signal it is not clear that there is correlations. So we this signal has been taken from one publicly available database, that is physionet database, and we have decomposed that signal, and I have shown few modes here. That same signal I have shown here, ECG 1, 2 and breathing and seismocardiogram signal in the top row, and in below the corresponding intrinsic mode function I have shown 10, 11, 12 up to 14 intrinsic mode function I have shown. So after decomposition you can see that this IMF 11 have similar frequency component, similar and have similarity for ECG 2 and breathing pattern here I have shown, and this seismocardiogram signal. So by observing the signal it will not be clear. So the correlation can be found by only using multivariate decomposition. Now I have compared the computational complexity of the proposed multivariate iterative filtering with the existing other multivariate techniques. Like for multivariate empirical mode decomposition has been, we have taken the signal, a 15 channel signal of length of sample length 6250, that is corresponding to 25 seconds of EEG signal, and we have decomposed that signal using all this algorithm. So multivariate empirical mode decomposition has taken 119.18 around 120 seconds to generate 14 IMF, and this MBMD multivariate variational mode decomposition has been taken 923.2 seconds to generate 14 IMF. And another variant of this multivariate first iterative filtering are there, that takes 4.74 seconds to generate 20 MIMF, and our proposed technique has taken 3.05 seconds to generate 21 IMF. So computationally our algorithm is much more faster. So now EEG, basically we will discuss the application of EEG signal. So EEG signal is the electrical activity of human brain that can be recorded from different part of the brain. In our brain there is four primary lobe, that is frontal lobe, parietal lobe, occipital lobe and temporal lobe, and these different lobe are responsible for different kind of activities. Like occipital lobe is responsible for visual processing, whatever we are observing or seeing, that has been that are processed in this occipital lobe. In the sensory motor area, in this junction of frontal lobe and parietal lobe, that there exists sensory motor cortex area that process the sensing different sensing organ, like we are the temperature different sensing sensing process has been taken place, and in motor area different motor activity are controlled from that, like hand movement, tongue movement, any kind of movement are controlled by this area. So to assess the activity of different parts of the brain, we record the electrical activity from all over the scalp, and the different standard position, that is there is 1020 international standard for recording EEG signal. So in frontal lobe there is FP1, FP2, FPZ, F3, FZ, and for temporal lobe there is T3, T5, T4, T6, and in central region C3, CZ, these electrode are placed, and in O1, O2, OZ are records the activity of occipital lobe. So by analyzing this EEG signal, this multi-channel EEG signal, we can gain access about the activity of different part of the brain. So today we'll discuss two applications. One is schizophrenia detection using multi-channel EEG, and another is motor imagery BCI. That is also using multi-channel EEG signal. So briefly, I will describe what is schizophrenia. Schizophrenia is a chronic mental neurological disorder that affects around 20 million people in world, and that is 1% of world population, and more than 1 million people in India. And this is a serious problem, uh, serious problem, and one of the major neurological disorder. The symptoms of this schizophrenia can be categorized in two categories. One is positive and negative. And positive, that is not happening, but it is the patient can observe, like delucination. The patient may believe something that is not true, and hallucinations, experience of seeing, hearing, tasting, smelling, or feeling any kind of sensory activity that does not really occur. And negative means some reduced effect, like motor behavior may be reduced, and lack of thinking, reduced speech may be in negative kind of symptoms of schizophrenia. And this schizophrenia cannot be cured. Till now there is no permanent cure for this disease, but on time treatment and diagnosis and followed by treatment can reduce the effect of this disease. So, and to diagnose the schizophrenia by observing the EEG signal or any kind of test, there is no specific test. By behavioral observation, or by knowing the patient's history, medical history, everything, by studying, neurological expert can diagnose only. But there is lack of neurological expert in our country and on over the country. So on time diagnosis is very difficult, and due to that we can't provide proper treatment to the patients. So if we can provide any kind of automatic solution for diagnosis, then that will be helpful, and on-time treatment can be started. So we have proposed here one method framework for of schizophrenia from multi-channel EEG signal. So here we have taken multi-channel EEG signal. This is the block diagram of the proposed framework. Briefly, we will discuss and what are the different steps included. So first we take a small segment of EEG signal, then we'll pre-process to improve the quality of the EEG signal. Then we have decomposed the EEG signal using multivariate iterative filtering into several modes. Then based on the mean frequency, we will group those modes into rhythms, EEG rhythms. EEG signal can be divided into five main EEG rhythms based on their frequency component, like 0.5 to 4 hertz component, frequency component can be termed as delta rhythm. Then 4 to 8 can be termed as theta rhythm. 8 to 13 can be termed as alpha rhythm. In this way, different frequency band can be termed in different rhythm. And that signifies different activity of the brain. So we proposed a automatic rhythm separation, adaptive rhythm separation technique here. Based on that, we obtained the EEG rhythm from also that is multivariate EEG rhythm, and from that we extract different features from those rhythms, and based on machine learning classifier, uh, we will classify this healthy and schizophrenia EEG signal. So we have used one publicly available EEG dataset for evaluation of the proposed framework that contained EEG signal corresponding to 14 patients and 14 healthy EEG signal of 14 subject. And those EEG signal has been recorded from 19 position like FP1, FP2 that I have already described. The sampling frequency of the signal was 250 hertz and duration was 15 minutes from each participant we have recorded. Here I have shown EEG signal corresponding to three channel FZ, CZ and PZ, and that signal I have decomposed using our proposed multivariate iterative filtering, and the second, third and fourth component I have shown here, and the corresponding frequency spectrum I have shown here. This is a frequency spectrum for channel original EEG signal, and this is the frequency spectrum corresponding to MIMF2. This is the third MIMF, and this is the fourth MIMF. So the from spectrum, it can be observed that the frequency content of all three channel is similar, and that is mode alignment property. So after that, after decomposing the EEG multi-channel EEG signal, we calculate the mean frequency of all the MIMF, and based on the mean frequency, we have grouped those MIMF together to obtain different rhythm. Like for if the mean frequency lies between zero point 0.1 to 4 hertz, then we sum up those MIMF to get delta rhythm. In this way, if the mean frequency lies in between 4 to 8 hertz, then we sum up those MIMF for obtaining theta rhythm. In this way, the all five rhythms we have obtained, and here I have shown delta, theta, alpha, beta, and gamma rhythm of the EEG signal. And from those rhythms, we have calculated three different statistical measures, that is Hodge activity, Hodge mobility, and Hodge complexity. And the mathematical formula is I have mentioned here. So we basically obtained 19. We have considered 19 channel EEG signal and 5 EEG rhythms and 3 Hertz parameters. So 285 features. So this thing I will when I will discuss with MATLAB code, it will be much more clear. And here I have shown the mean value of different features for healthy participant and for schizophrenic participant, and we have performed student t-test. That's basically how those features are independent to each other, that can be tested, and based on the p-value of student t-test, we have ranked those all features, and base 30 feature we have chosen by preliminary examinations, preliminary experiment. And then if the dimension of the feature will be less, then the complexity of the classifier will also reduce. Here I have shown the best most significant 10 features. Here it can be observed that the feature value of this healthy and schizophrenic EEG are different. And now based on this different number of features, we have trained SVM cubic classifier, and here in x-axis I have shown the number of features we have considered for classification, and in y-axis I have shown the obtained accuracy, classification accuracy. So for when we have used very less number of features like 5 features, then the accuracy is very low. But when we use 10 features, the accuracy has been increased significantly, and up to certain number of like around 30, the accuracy has been increased, then it has not been increased. So we have determined that 30 feature is sufficient for prediction. So using 30 number most significant features, we have developed different machine learning classifier, that is SVM with cubic kernel, is support vector machine with quadratic kernel, SVM linear kernel, linear discriminant classifier, KNN, and decision tree classifier. And this parameter has been computed, this statistical parameter, to assess the classification performance, that is accuracy, sensitivity, specificity, and PPV, positive predictive value. Here I have shown the classification performance for 5-fold cross validation and 10-fold cross validation. So for SVM cubic classifier, we have obtained highest accuracy 98.9%, that have standard deviation zero point 0.9, and this is the 99 percentage sensitivity, specificity of 98%, and positive predictive value of 98%. So we have chosen this we have suggested this SBM cubic classifier with our proposed framework for the identification of schizophrenia from EEG signal. Here I have compared the obtained performance with state of the art method. So this proposed method can be broadly classified into two categories. One is machine learning based method, and another is deep learning based method. So machine learning based method are computationally less complex and require less amount of training data, and also it consumes for deep learning, it takes a lot of data it requires, and also takes higher amount of training time. So machine learning based classifier, for if we can properly choose the feature, the significant features, then we can design a system with lower complexity. So here you can see that this our proposed method have obtained 98.90% accuracy, and here like this method as proposed by O et al in using CNN has also attained similar accuracy. And like this method also use CNN, like Aslan et al has proposed in 2020. They have obtained 97% accuracy, and another method proposed by Chandran et al in 2020, they have also obtained accuracy 99.1%. So our machine learning based method have obtained similar kind of accuracy to deep learning method, deep learning based classifier. So those method have directly used raw EEG signal, most of the method, but our machine learning method is driven by signal processing. Signal processing has helps to extract significant features, and then based on those features we have trained classifier. And the second application we will discuss based on the motor imagery BCI from EEG signal. So imagination of motor movement, like left hand movement or right hand movement, there will not be any real movement, but instead imagination of left or right hand or tongue movement or leg movement. So this can be used to for rehabilitation application who have some problem with their peripheral nervous system, some motor part may be damaged due to some accident or some diseases. Then we can use this MIBCI system to extract alternative signal from brain itself. So we can that patient can communicate with the external world using this system. So here I have shown a representative figure that explains the needs of BCI. So if there is a problem in this peripheral nervous system or motor path here, then that subject may be paralyzed. So they cannot control their arm. So if we can extract the command from their central nervous system, then based on signal processing and we can decode that signal and generate some command for controlling device, then we can provide some level of movement to that patient. That is basically brain computer interfacing. And this kind of paralytic patient due to different diseases like different or due to stroke or trauma accident, there exist huge number of patients who cannot move their arm of any or leg or any peripheral devices. So these MIBCI devices may help them hugely. And this except EEG signal, there are several neuroimaging modalities like functional magnetic resonance imaging, magnetoencephalogram, transcranial magnetic stimulation, positron emission tomography, PET, etc. So over those, EEG signal have some advantages like EEG signal have for that EEG signal has been widely studied for this application. EEG signal first of all can be recorded non-invasively. It has potential in anywhere it can be recorded in ambulatory or in outdoor condition. EEG signal can be recorded. EEG signal provide very high time resolution. That means if we set the sampling frequency 250 hertz, then the we assess the brain activity 250 times in 1 second, and that is not possible for various other neuroimaging technique like fMRI. And the cost of the EEG is recording is comparatively very low as compared to other techniques. And already I've mentioned that it can be recorded outside lab also. And for assessing our for evaluating our proposed MIBCI method, we have used two publicly available dataset, BCI dataset. The first dataset, BCI competition 4 2A dataset, that have that have been recorded from 9 subjects corresponding to left and right hand, both feet and tongue movement. So from EEG signal, we have classified the EEG signal whether it is corresponding to left hand movement or right hand movement. So we can generate a command corresponding to that. So signal has been recorded from using 22 different electrode position channel, and 250 hertz sampling frequency was set. And signal has been recorded using 288 trials. That is for left hand movement there is 72 trials for each movement. Right hand movement also 72 trials are there, and total 288 trials are there for each subject. And the timing diagram of the experiment I have shown here, like one on a screen, a large screen was fixed in front of a subject, and one beep was sounded to instruct the subject, and one fixation cross was appeared around -1 second, and at 0 second means 0 second we have marked the time when the instruction to imagine the movement was presented to the subject, and before means fixation cross was appeared 1 second before, and beep was played before 2 seconds. So in that way we have recorded the EEG signal from dataset. So we have taken from -1 second to 2 second for multivariate detector filter and decomposition, and the feature these special features we have For computing point modes, and they are related. We have used two data set reliable data to to evaluate our proposed framework. This is the block diagram of the proposed framework. We first taken multi-channel EEG signal, then we have pre-processed. In pre-processing, basically we have used one notch filtering, so to remove line noise. Then we have decomposed using multivariate filtering, and from each mode we compute this CSP features. The CSP widely used for design. We have randomized feature and select most significant feature. Based on that, we trained machine learning classifier. And in the validation, there was completely an different session recorded from the subject on day validating, and on that validation part we repeat the same procedure, and the weight we calculate from the training session used here, and to extract the features, and based on the index of the selected feature, we have again selected those features from in evaluation part, and based on that, on pretend classified, we have classified this event EEG signal into two categories, that is class 1 and class 2. Class 1 may be we have trained binary classifier like left or right hand movement or left or tongue movement in this way. So pre-processing, we have segmented the EEG signal. Then we have used 50 Hz power line noise, 50 Hz power line removal filter, and this CSP filter is very sensitive to noise, and due to small perturbation, this performance may be reduced. So in during training, we have used the line filter to remove the 50 Hz noise, but for evaluation part to show the effectiveness of our proposed methodology, we didn't use this 50 Hz filter to check the robustness. Here I have shown the algorithmic representation of the multivariate iterative filtering. The multivariate iterative filtering already I have discussed, so I am not going in detail into this framework, this algorithm. So after decomposing, we extract the common spatial filtering to extract the feature from the different MIMF. In common spatial filtering, basically we that is one spatial filter. The spatial resolution of the EEG signal is very less. So by using this, we can improve the spatial resolution. We can get higher spatial resolution, and this W is the spatial filter, and we can transform that W X, the original signal, using W to obtain the spatially filtered signal, and the variance of those Z can be understood as features. In CSP, basically it increases the variance of for left hand, it may provide average row 1 and provide low variance for last row, and it will be completely opposite for opposite class. For right hand, maybe the first row will have low variance, and last row will have higher variance. So the variance can be a useful feature, and based on the variance of different MIMF, we trained linear discriminant analysis for classification of EEG signal. Here I have shown the EEG signal, multi-channel EEG signal C3 corresponding to 3 locations classification C3, CZ, C4. Then I have decomposed into MIMF, and I have shown 4 MIMF here. And event related desynchronization and event related synchronization is a very important phenomena in motor behavior, like motor or sensory behavior. So sometime during motor movement, the ERD means the brain activity will be desynchronized and will get lower amplitude in signal. And when sometimes it will increase synchronized activity, that is ERS, and for that we will get increased alpha rhythmic activity. So our result will show that this MIMF will help to observe this ERD and ERS much more clear than original EEG signal. From original EEG signal, it will not be clear that whether ERD or ERS is occurring, but from signal, it will be clear. Here I have shown different the frequency range of different MIMF, as this is a completely data adaptive technique. So the range of this the frequency range is not fixed for different MIMF. So using box plot, I have shown the range. So the low frequency range for all the IMF, and this is the highest frequency range for first IMF. And as MIMF, first IMF has higher frequency content, higher frequency. So you can see this is a low frequency range, and this is this first MIMF from all channel lies in between this range. And this second IMF lies in this range, that is comparatively lower than first IMF, and third IMF is in this range, and this fourth IMF lies in this range. And using this cyan band, I have shown the alpha rhythm range that belongs to like 8 to 15 hertz. So in alpha band, this third and fourth IMF lies, and this alpha band is can show that this ERD and ERS activity. So this later we will show that this third and fourth IFM will show distinguished pattern. Here I have shown the classification accuracy for the first data set we have considered, VCI for 2A. For left and right hand tags, we have obtained this accuracy for different subject, and we have obtained this is the average accuracy, 83% accuracy. For left hand and feet, we have obtained average of 86.19 accuracy, and this is the accuracy for second databases. That second database contained the EEG signal for 3 subject, and for that we obtained accuracy of 84 point average accuracy of 84.4% for left and right hand tucks. For left and feet tucks, 85% accuracy is there, and for left and tongue, there is we obtained 94% accuracy. In this way, for different tongues, we obtained a different accuracy. For left and tongue, left hand and tongue movement has been discriminated with highest accuracy, 94.26% accuracy, and feet and tongue movement cannot be identified very with very high accuracy. That is 77% accuracy. Here I have shown the effect of selecting different number of features on accuracy. So for different subject, the evaluation of accuracy has been shown using different lines. And we have compared our proposed method on the state of the method, like when CSP method has been proposed, and it has gained a lot of attention and popularity, and primarily it has been applied on raw signal, that is bandpass signal, 4 to 40 hertz signal. And we will compare the performance of our proposed method with this state of the method. Then another modified method has been proposed, that is filter bank CSP, that using bandpass predefined frequency band, uh, and they divided the EEG signal into several bands of each band have bandwidth of 4 hertz. Then another method has been proposed, that is WLTL. Then MEMD based method has been proposed, that multivariate empirical mode decomposition has been used for removing the noise. Then sliding SSMEMDBF has been proposed, and Riemannian geometry has been used for feature extraction. Then sliding window LCR has been proposed, and another method TSGSP, temporarily constant sparse group spatial pattern, has been used for MIBCI application. So we have compared the performance of the proposed method with this all state of the method. So here for CSP, they provide 76.23 percentage accuracy for left and right hand tags, and APCSP has given 69% accuracy. In this way, I can obtain that. I can see that our MIF CSP method has provided 83.18 accuracy, that is highest accuracy for this left and right motor imagery tags identification. And in this second table in this slide, I have shown the average accuracy only for different motor imagery tasks. For left hand feet and left hand tongue, right hand feet, right hand versus feet movement, have provided highest accuracy, that is 86.19%, 88.27, and 85.65% accuracy. But for right hand and tongue movement, this SSMEMD RG, Riemannian geometry based feature, MEMD and Riemannian geometry based features framework has provided highest accuracy, but our method also provide quite similar accuracy. And for feet and tongue, feet movement and tongue imagery movement, this TSGSP framework has provided highest accuracy, and all other method has provided comparatively less accuracy. Here I have shown the the topoplot of the extracted features and the feature space also. So earlier I have discussed that MIMF3 and MIMF4 is lying in the range of alpha range, and this alpha is responsible to this motor movement. And from this topoplot is the feature value is shown using topoplot, and in the top row I have shown the feature value corresponding to different MIMF for right hand movement, and next row I have shown the feature value corresponding to different MIMF for left hand movement. So here for and from this topoplot, by observing this, if there exists significant difference between this left and right hand movement, you can say that this region may be affected due to motor imagery movement. So for these first two topoplot, this one for MIMF1, MIMF2 does not have any significant difference, but MIMF3, if you observe that MIMF3 and MIMF4 is quite different. Here this have very high feature value corresponding to this one. And if you observe the feature space, two significant features I have used to construct the feature space. So MIMF 1 and 2 is not that cannot provide that much discrimination, but MIMF 3 and MIMF 4 properly discriminate these two classes, this left hand and right hand movement classes. So this MIMF 3 and 4 band that has been extracted adaptively, that is useful for motor imagery movement identification. And here I have shown the computational complexity that is already I have shown. And different algorithm I have used for comparing the performance of the MIMF, like MVMD and MEMD I have compared. So the classification accuracy is we obtained a highest classification accuracy for all cases, like left hand, right hand movement, left hand feet movement, and all other classification cases. Our proposed MIMF based method has provided highest accuracy. So here the proposed schizophrenia detection method has shown that the machine learning based method have provided the accuracy, the performance similar performance as compared to CNN based method. But CNN based method already have mentioned that computationally very expensive. So machine learning based method is advantageous in that manner. And the mode alignment provided by the proposed MIF technique is proper, that I have described using uh, the spectrum of the decomposed EEG signal, and based on the decomposed, and in second application the decomposed MI multivariate intrinsic mode function is used to extract the feature CSP based feature, and that so very good and promising performance for MIBCI application. So this is the reference. Now we'll go for this tutorial part. So if, up to this part, if anyone have any doubt, then you can ask. Then we can start the tutorial session. So if you have you any doubt, participant?
If anyone is having any doubts, please interact with Mr. Das.
So if you have you any doubt, participant? Okay, if no doubt, we can start our hands-on session. So I'll describe the schizophrenia detection part that I already have discussed. So I have shared one link, Google Drive link. So if you have MATLAB, you can follow me for signal processing part. So you can download the code from that shared link, and that is also available on GitHub also. So GitHub link also I have shared. So can you tell me means how much participant have access with MATLAB, so that you can parallelly run, and if you have any face any problem, then I can you can ask.
Actually, I have no idea about that. And currently, what I know,
Okay, so if participant doesn't have,
everybody
then
is
I
using
can show
Python.
from my MATLAB.
Yes, you please do that. And you can share your code. So whoever is
Yeah, code I have
using
shared actually.
MATLAB, they
Participant is
can try it afterwards.
okay. Some participant is asking for
They can try
this
out.
drive. I have shared the link this for code today's tutorial. basically schizophrenia detection.
Okay.
Some participant is asking a link for what. And this GitHub code is for multivariate iterative filtering, the MATLAB code. So you can
Okay.
download, and
Okay.
then I will discuss the signal processing part using MATLAB. Then I will extract the feature, and I will upload that. I have uploaded that feature in Google Drive. So classification part, everyone can try it by yourself. That that is in Google Colab. You can try. So should I start to describe the MATLAB code using my MATLAB by presenting my screen?
Yes. You please go ahead.
Okay, thank you, ma'am.
Excuse me, sir. Am I audible?
Yes, yes, please.
Sir, just I have a query. You have done it in MATLAB or in Python? Google Colab is with Python, right?
Yeah, the signal processing part, actually, I have done in MATLAB, and classification part I can also show in MATLAB. But I also later using those extracted feature, the classification part I will describe in Google Colab also, so that everyone can follow. I think Google Colab anyone can access.
Yes, yes. Okay, okay, sir. Thank
Okay. Actually, this library is only available for MATLAB, the signal processing part. For that,
Okay, sir.
okay. So if anyone is following if they have MATLAB, then they face some problem, they can ask in between. And the MATLAB code can be downloaded from this drive link. And please add this folder and subfolder to your MATLAB path before running the code. So is it visible? Is my
Yeah.
screen is visible?
Yeah, yeah. It is visible.
Yes, sir.
Okay, thank you. So this is the basic block diagram of the proposed framework that I already have discussed. And now stepwise I will discuss the MATLAB code for every block. And this classification, the all the part up to feature extraction, I will run in MATLAB, and after that I will upload that feature in my Google Drive, so that this classification part can be done in Python, and everyone can do that by their own. And this is the paper we have published based on this framework. And the database available, and the reference for the database, EEG signal database, is this one. So here basically you can if you want, you can download the folder from Google Drive link. So that in that folder, one EDF read folder is there, subfolder is there, that helps to read the EDF, the EEG signal, that is basically in EDF format. And this MIF folder will contain the MATLAB code for multivariate iterative filtering. And this schizophrenia detection, this is the main today's tutorial code, the schizophrenia detection one that I am here running. So if we run this segment, first it will read the data. corresponding to first subject, that is 801 EDF. And the data I have already provided for only for two subject I have provided. If you want, you can download from the original papers link, the remaining subject data. And this line helps to read the EDF file in struct HDR struct and as a signal struct. Then we have segmented the EG signal of into small segment of each segment will be of 25 seconds. Then we will decompose the signal into using multivariate iterative filtering. So we have chosen here the signal in this x variable. So then we will decompose that signal in using iterative filtering this function. So it takes 1.73 seconds to decompose the signal, and I'm trying to plot those signals. Now we can see that for example, that is we have used all 19 channel signal from the databases, but only 3 channel has been I have chosen to for visual representation. This first row represent the easy signal, and the remaining row are for different MIMF corresponding to that signal. This first column for channel 1, second column in channel 2, and third column in channel 2, channel 3. So this decomposition plot is clear. Uh, if it is clear, then I will go further. That is rhythm separation from that EEG decomposition from that multivariate mode. If anyone is following by their they are running their the code by them, then it may take some time. So please ping me, I will wait, and if you finding any problem, then I will try to solve. So after decomposing the signal, here I have taken one loop. Previously, I have shown taken only one segment and decomposed that and show the result. But for running whole EG signal, I have written a loop here. So in that loop, I have read the signal of all subject, all different subject. We then segmented out the signal. Then using the proposed multivariate iterative filtering, we have decomposed those signal, and then we have stored the decomposed component for all the segment. In the next block, I have decompose the EEG signal corresponding to schizophrenic subject. Then in for rhythm separation, we have computed the mean frequency of each rhythm, each MIMF, so that based on that mean frequency, we can categorize the MIMF and add those MIMF to obtain that particular rhythm. For example, like for delta rhythm, if the mean frequency lies in between zero point 0.1 to 4 hertz, then we select those MIMF and we add all the MIMF to obtain the delta rhythm. Here I have written the code for summing up those MIMF to obtain the rhythm, particular rhythm. This all five rhythms, 1, 2, 3, 4, 5. Then from each rhythm, we compute the Hertz parameter, that is activity, complexity, and mobility. And based on those from all channel and all rhythm and 3 Hertz parameters, so we will get total 285 number of features. And the healthy features, I have termed that as zeroth class, and we labeled the schizophrenic one as 1. So in that way, we have construct the feature matrix and corresponding to class matrix. You can see this feature matrix. We have arranged the healthy EG segment, and corresponding class can be seen here. And for schizophrenic participant, their class level is 1. And I have saved the feature matrix and class matrix. So from that drive link, you can download this feature matrix. I have provided that feature matrix so that you can design the classifier also. The I have named the feature matrix as feature CSV. And class CSV for class matrix. And based on that feature and class matrix, we can train the classifier. So if you have access to Colab, then you can upload that feature matrix and class matrix to train the classifier. So are you able to download the feature matrix? Am I audible? Am I audible?
Yes, sir. You are
Yes,
audible.
yes, you're audible.
Okay, okay, thank you. So, can you please tell me that whether you can download that feature matrix so that we can continue with collab? You can, if you access this folder, this drive link, then two feature matrix are there. Sorry, one feature matrix and one class matrix is there. Okay, here you have to upload this two file. One is class file and that contain the label of each classes, and another feature matrix. So we'll train machine learning classifier SVM classifier based on this feature matrix and class matrix. So for importing data, we will use CSV library, and here I've included the required library. Then I will I have read the input data feature matrix here, and you can observe that feature matrix size is 151 sample is there for two classes, and 285 features are there. In data X, I have loaded the feature matrix, that is 151 sample are there and 285 features are there, and in data Y, uh, the class label is there, so there is 151 label corresponding to each sample, and some nan value has been there, so we have replaced the nan value using zero value in feature matrix. Then using holdout validation, we have taken 70% of data randomly. We have chosen randomly 70% data for training and 30% data for validation. And based on those, we have trained SVM classifier with linear kernel. So here you can see that we are getting the performance of 97%, and this has been this feature has been taken only from the first subject of two subject, first two subject. And for cross validation, here we have performed that five-fold cross validation. So for the accuracy for all five fold is showing. For first fold it is giving 97% accuracy, and for all other fold it is giving 100% accuracy. So if we take the average accuracy, then we'll get around 98%, 99% accuracy. So if you have any question, you can ask. Like, otherwise, I have shown by running from my side.
Any questions? Okay, you please go ahead.
Okay, the, for same classification part can be done using MATLAB also. So in MATLAB, it can be done. There is one app is available. I'm trying to open the classification learner app. It is taking some time. Using this, I have load the feature matrix and the class level corresponding to that in workspace. So from workspace, I have selected this feature matrix and class level matrix corresponding to that feature matrix. Then I have for 5-fold cross validation I have chosen. So here we can choose various classifier for classifying the data, this feature. So we can choose this linear SVM classifier we have chosen from the list. So based on that 285 features, we can train. So this linear SVM is providing 99.3% accuracy. This healthy only one health event has been classified only as zero. And so only one schizophrenic event has been classified as healthy one. All other event has been classified properly. And here you can do the feature selection also. So we have used this Kruskal-Wallis test-based ranking can be performed, and few features like 50 features can be chosen from all the features, most significant 50 features. So based on that also we can train the same classifier. So here you can observe that using only most significant 50 features we have trained, and then also we are getting similar kind of accuracy, 99.3% accuracy. So this is the confusion matrix, and ROC curve you can observe for every model. So as we are getting same accuracy though, so then we can use less number of features, most like 50 more in our application we have suggested 30 most significant features is sufficient for predicting schizophrenia from EEG signal. And from this app you can export the classifier model for further classifying the other epochs using this option. So actually, I have already presented the whole procedure of schizophrenia detection from EEG signal. So if you have any doubt, you can ask. Otherwise, I have presented. Now you can, if anyone have any doubt, you can ask. You can download, and you can try by yourself later, and if you find problem, then later also you can contact. The code is available, the multivariate filtering code is available in GitHub also. Actually, I have shared the Google Drive link. Again, I am sharing. So if you have MATLAB, you have access to MATLAB, then you can download and try the whole code. And if you do not have MATLAB and you are only trying to uh, go for classification part, if you want to try, then you can use the feature part. That two feature means like feature matrix and another is class matrix. So from that you can train machine learning classifier on Python also in Google Colab or any other platform.
No.
He's saying something, huh?
Hello, ma'am. Actually, so I have
Yes.
demonstrated the framework and
It's over. You completed.
yes, yeah.
Oh, okay. Okay. So, any question, participants? Anybody is having any question? Okay, so all materials is shared with you. You can find in the chat box. So you can practice or you can use it. And afterwards, if you find any problem, encountered any kind of problem, you can contact Mr. Das, and I request Kritiprasanna Das to share your mail ID so that if
Yes, yes,
anyone wants to contact you, they can later they can contact you.
yes, ma'am.
And also we have given a link for a multiple choice question, and all the participants are requested to submit the answer of the question by before 10 p.m. tonight. So thank you, Mr. Kritiprasanna Das, for giving so much time. So now I request Imli Tosi Jamir to offer a vote of thanks.
Thank you, ma'am, for the opportunity. And I have shared the mail ID. So if anyone have any question, then I'll be happy to discuss.
Okay.
Okay, thank you.
Okay, thank
Um,
you. Yes, thank you, ma'am. Okay, and thank you,
yeah.
sir. Okay, so we'll be ending this session. But before we end this session, on behalf of all the participants here today and the organizing committee, we would like to extend our sincere gratitude to our speaker, Sir Das, for imparting a valuable knowledge. He has been so patient and so patiently teaching us all the things that he has learned so far, And we also appreciate the effort and time that you have put on sharing your expertise with us. Once again, thank you for being a part of our seminar and making this session a very productive one. Thank you so much, sir.
Thank you so much.
Thank you. Thank you so much.
Thank you, ma'am.